Thank you so much for joining us today. My name is Chris Renton. I am the Associate Director of Marketing and Communications here at the Yale Peabody Museum. I want to welcome you all today to our second consecutive one of these talks on a Thursday afternoon. To those of you in New Haven or the Connecticut area, thank you for giving up another Thursday, 45 minutes of your Thursday afternoon of beautiful weather. It's absolutely gorgeous outside, so thanks for giving that up to come in and be on the internet for a little while longer today. Some ground rules real quick. You'll notice that the chat is off, but the Q&A function is available to you at the bottom of your screen. If you have any questions during the presentation, feel free to ask them there. We will have a Q&A portion at the end of this talk. And I sort of have to thank you up front for your understanding that we won't be able to get to everybody today. But anything that we don't answer, please do feel free to send to us via email or on social media. Those are great ways to keep in touch with us as well. And if you follow us on Instagram, Twitter, or Facebook, or sign up for our email list at our website, you won't miss anything. Someday we will be able to do live events again at the Peabody Museum. We're all looking forward to that. We don't know when that'll be, but until then, we'll do as many of these online talks as possible. So without further ado, I want to introduce our speaker today, Matteo Fabbri. Matteo, if you want to turn on your screen real quick, just to make sure that I'm hearing, you can hear me.
Hey, everyone.
You're there. This is Matteo Fabbri. He is a PhD candidate in geology and geophysics here at Yale, working under his advisor, Dr. Bart Ongen-Buller, who is also a curator here at the Peabody Museum. Broadly speaking, his research focus is on the dinosaur to bird transition, hopefully illuminating the origin and evolutionary history of our crown bird species. His CV, I speak from experience, is impressively long. So I'll try to just glaze over it and let Matteo speak a bit more about his experience during his presentation. His fieldwork has taken him around the country, including Arizona and Florida, and then around the world, really, to places like Spain, Romania, and then today he'll be talking to us about his experience in Morocco, most recently. While at Yale, Matteo has been awarded the 2019 William Ford Prize, and in 2018, he was given the Simpson Award for the best research article published that year. He's also a recipient of the Hutchinson Memorial Fellowship. He has a number of articles currently in review, and he is published as an author or co-author in at least 16 papers. Most recently, he was published alongside one of our previous guests, Yasmina Viman, in Nature and Paleontology. Thank you very much, Matteo, for joining us today. And I'll let you tell everyone about your latest research on our good friend Spinosaurus.
Thank you for the introduction, Christopher. And now I will share my presentation with all the viewers, and I will get started. And so today we will be talking about Spinosaurus, which is this charismatic dinosaur. And I want to get straightforward to it. All tetrapod major groups, meaning all those animals that have 4 limbs, evolved aquatic forms. In particular, if we are familiar with whales or with seals, and these are, of course, a part of the mammal branch. Marine turtles, reptiles explore the sea with forms like mosasaurs and ichthyosaurs. I guess everyone is familiar with archosaurs, meaning crocodiles. And also birds evolved aquatic forms, such as penguins and cormorants, and other forms that are more playing with water, like herons, that are not directly living into water, but inevitably are dependent from the resources in this environment. For reasons we still don't fully understand, dinosaurs never got to the waters. So we are kind of familiar with dinosaurs, like the long-necked dinosaurs that are the sauropods, ornithischians such as ankylosaurs and duck-billed dinosaurs, and of course predatory dinosaurs. All these groups never went to water, or at least is the kind of idea and hypothesis we currently have. Only exception to this environmental restriction to dinosaurs seem to be birds that are the actual descendants of predatory dinosaurs that managed to evolve flight and then get to conquer the skies. The goal of my talk today is to challenge this hypothesis and to demonstrate to all of you that indeed until 3 weeks ago, we finally found the first semi-aquatic dinosaur. Our story begins at the beginning of the 20th century, where with Ernst Romer. He was a German paleontologist who had a huge influence in the field. He was a sort of pioneer in the sense that he was among the first people who really went to Africa and the Sahara Desert in particular to explore the geological record to find out new dinosaurs. And indeed, in all his expeditions that will be between the beginning of the 20th century until 1920s, more or less, he found a huge amount of new specimens and, of course, new dinosaurs. Among these dinosaurs, probably the most famous is Spinosaurus aegyptiacus. You can see already that even though this dinosaur is dismembered in different bones and it's not fully complete, but definitely you can recognize some characters that make it unique. First of all, the long spines along the vertebrae. This is why it's called the Spinosaurus. And then this is slender jaws that are almost unique to this dinosaur with the presence of conical teeth. Now, Stromer thought about the first reconstruction of this dinosaur, and there are several unique features that makes it peculiar. So regarding the jaws, Stromer suggests that these jaws are perfect to catch slippery prey, such as fishes, for example. He also noticed that the long spines were forming this gray sail on the back of the dinosaur. And he also noticed that this animal was really big. Indeed, he noticed that most probably this dinosaur was bigger than T-Rex, which was described just 1 decade before. However, Stromer's life was about to get a sudden turn. During the Second World War, in 1944, the British Air Force bombed Munich, where Stromer was working at the museum and where all his African collection was housed. So during this Air Force bomb, all the collection got destroyed. So Stromer lost all the material that made him famous. And also his private life got hit pretty hard, in the sense that Stromer had 3 sons. All of them fought in the war, and 2 of them got killed in the front line. And the third son got captured by the Soviet Union and managed to come back to Germany only in 1950. Stromer will die in 1952. So during the Second World War, the entire legacy and career scientific contributions Stromer built during his life got deleted and almost forgotten, and his private life will never come back to the happiness that he had during the beginning of the century. In the last decades, especially between the 80s, 90s, and the early 2000s, several new Spinosaurs were found. These are relatives of Spinosaurus, and all of them have a unique character in common. This is the long snout slender jaws with conical teeth. In some cases, we got lucky, like with Suchomimus and Baryonyx and the Ichthyovenator from Asia. And in this case, we obtained more or less complete skeletons, but the majority of these remains are fragmentary. Anyway, all these discoveries were really important because they gave an insight regarding the evolution of Spinosaurus. And of course, scientists figured out these animals most probably were playing with the water. And the current hypothesis was that these animals were probably staying in front of the rivers, hunting like herons, so waiting for fishes to pass by to then strike with the snout and catch them. Regarding Spinosaurus, several other finds appeared in Morocco and North Africa in general, in Egypt, Algeria, Tunisia. However, all these finds were extremely fragmentary. Like we could find single isolated bones, single vertebrae, a lot of disarticulated teeth, and so on and so forth. So nothing that could actually be compared with the skeleton that we lost during the Second World War and that Stromer found. And this would be an incredibly important step forward in the field because it would give us a new idea about the anatomy of this animal. We will find a new specimen to attribute the species, but also could illuminate us regarding its ecology. Before I get to the discovery of this new skeleton, I want to express the fact that everything you are about to see was the result of a true teamwork. This team encountered institutions and experts from all over the world. And the reason we needed a true teamwork to examine this new skeleton, it's because we wanted to understand the functional morphology, the growth, the ecological adaptation of this animal, and of course its anatomy. And we also had the privilege to work with scientific illustrators and paleo artists that really helped to bring this dinosaur back to life, as you are about to see. And this was really important because independently from the methodology applied or the type of evidence we were finding, the results that came out from this study were pointing all at the same result and interpretation of the animal. In the last 10 years, we went to Morocco in the Kankem, which is at the border between Morocco and Algeria. It's basically the door of the Sahara Desert. And we were digging in the Cretaceous rocks that are abundant in this area. As you can see, it's a place which is pretty arid, and temperatures are really high. Like it's not rare that the temperatures are beyond 120 Fahrenheit during the day. And this is more or less how our day goes by. During the day, we are digging and climbing hills, hoping that some bones are sticking out. And then we eat canned food, and then we sleep on the desert in tents. And at night, we try just to catalog and identify the specimens we have. Of course, there are some real dangers out there, like venomous snakes, like the horned viper, or scorpions, sandstorms. So it's a pretty tough place to work in. But the reason why we are doing this, it's because this site, this region is incredibly rich in fossils. It's hard to believe, but the Sahara Desert we know today, 100 million years ago, was a huge river system. So it was pretty tropical in temperature and it was full of water. And we know this from the sediments that are around it that characterize the rocks of this area. And within these rocks, we can reconstruct a unique ecosystem that is unique not only in terms of Cretaceous, but unique to any other Mesozoic ecosystem around the world. And this is because it's incredibly rich of river organisms and incredibly rich of predators. So when we look at the assemblage of this ecosystem, we can see that the majority of specimens we recover from this area are giant fishes or small size fishes, including giant lungfish that are car size or giant sawfish that are as long as a bus. And around them, we found turtles, a huge diversity of crocodiles that could reach 13, 14 meters in length, an incredible variety of flying reptiles, the pterosaurs, and of this type of reptiles we find from small to medium to large size. And regarding the dinosaurs, the only herbivorous dinosaurs around are the long-necked dinosaurs like Titanosaurus and Diplodocus. We have a medium-sized Abelisaur, which is a predatory dinosaur. We find a T-Rex size predatory dinosaur called Carcharodontosaurus, and of course, fragments of Spinosaurus. Spinosaurus, which is constituting the majority of the fossils we found during our fieldworks in comparison to other predatory dinosaurs. And during these 10 years, we were able to basically collect fossils for each of these groups. And some of them are already published, some of them are still in preparation. However, it is obvious the masterpiece that we excavated in these years was a new skeleton of Spinosaurus. This skeleton was found up in this hill, in the middle of the Kenkem. So there is a horizontal layer going inside the hill. And we were able to dig this skeleton just working on and going towards the inside of the hill. So we had to take out the layers on top of the skeleton and then reach a layer, extract the bones, and then moving farther and farther inside the hill. It was a lot of work, really slow, but it was definitely worth it. The first question, of course, you might have is how do we know that this skeleton belongs to Spinosaurus? And the reason is that there are several bones that have anatomical characters that are in common and are shared with the skeleton by Stromer. For example, it has conical teeth, it has very long spines on the back, and also part of the tail, the proximal part, is very similar to the vertebrae that Stromer found. These are some pictures of the bones. Once we reach the layer, you can see how all these bones were basically articulated between them. In this case, they are tail bones, and it was really a lot of work to take them out. But it was worth it because at the end of the game, we knew that this was one of the best preserved dinosaurs ever found from mainland Africa. And when we started to mount a specimen and to prepare the bones and to start to understand the anatomy, we estimated that this individual was about 11 meters long, so really a big individual. However, it was not as big as the Stromer's individual. So we wanted to know if this animal was fully grown or not. And this is when Nizar Ibrahim, who is at Detroit University and leading scientist in the papers published on this specimen, and also the Museum of Milan with Simone Maganuco and Cristiano Dal Sasso, contacted me to understand the age of the individual and to understand if this animal was still growing. And how can we do this? We can simply cut the bones of the dinosaurs and check for lines of growth that I hope you are seeing here and also kind of highlighted with red arrows. These lines are annual lines of growth. So it's basically like cutting a tree and counting the lines to know the age. So you can infer the absolute age, and then looking at the spacing between these lines, you can understand if the growth was explosive, like a young individual, or if it was slowing down, so the animal was close to finish its growth, or if it was stopped, like spacing is so small that basically we can infer that the animal was fully grown. In the case of our skeleton, we saw that this animal was still growing at the moment of its death, and its age was around 17 years old, plus or minus 2 years, because we have to go through some methodologies and calculation that can bring some error. So we know that this individual was still growing, but so how big was Spinosaurus? So we based our anatomical reconstruction on the Spinosaurus we found, and also on the skeleton by Stromer, plus some isolated fossil remains that are around the collections in the world. And what comes out is that Spinosaurus was around 50 feet long. This means around 14, 15 meters long. And this makes a Spinosaurus by a long shot the longest predatory dinosaur ever lived, much longer than T-Rex. Also, I wanted to put two pictures of when we mounted the skeleton with two average people here. One is here working for National Geographic, and here is Simone Maganuco, one of the co-authors of the paper, and you can see that this animal is really big. However, size is most probably the least interesting fact about this animal. Indeed, the most peculiar thing that we could observe is about the proportion of the animal, and also this will give us a hint regarding its ecology. So starting from the skull, we can see that already the skull have some hint to a semi-aquatic adaptation. Indeed, we can see that all the jaws are pretty slender and elongated with conical teeth, exactly like crocodiles. And also there is this small opening that is the opening of the nose. And this opening is moved backwards in the skull. Now, this is something that we can observe, for example, in whales, where the nose is brought backwards in the skull because it allows for the snout to be submerged under the surface of the water and at the same time to breathe. Also, the snout is full of small foramina at the tips. And what these tips are is for the enclosure of neurovascular networks. In other words, the nerves are branching in this proportion in this dinosaur, very similarly to other crocodiles, for example. And this is because when you are within the water column, smell is completely useless for hunting, and you have to rely for something that is actually recognizable as an input for hunting prey in water. So the nerves at the tip of the snout allow you to have sensitivity for movements in the water. So it's kind of a location of the prey, like modern crocodiles actually apply. When we go to look at the postcrania, what we see is that the legs are incredibly short. This is very atypical in comparison to any other predatory dinosaur. Indeed, in T-Rex, like any other theropod, you can see that the legs are incredibly long. And this is because predatory dinosaurs were active predators and bipedal on land. Short limbs are usually linked to semi-aquatic adaptations. So we see a reduction of the limbs in whales, seals, hippos, penguins, and so on. But also the feet of Spinosaurus are very peculiar in the sense that they are very wide in comparison to other dinosaurs. And this is very useful when you want to walk on soft sediment or also to paddle in water. The same can be observed, for example, in ducks. We said before that we were cutting the bones of Spinosaurus to know the age, but when we were cutting the bones, we realized that there was a surprise inside. So all predatory dinosaurs, like a majority of modern birds, have hollow bones. You can cut a bone of a chicken or a turkey, and you will see that they are completely empty inside. However, Spinosaurus have very dense and compact bones. And this is something, again, that we see in animals adapted to water. For example, like in penguins. This is because when you enter into water, if you have hollow bones, you have a problem with buoyancy, in the sense that you will tend to float, and therefore you don't have an active control on your movements. Therefore, aquatic animals, like a Spinosaurus, had to increase their density in order to hunt within the water column. Histology also gave us some hints regarding the function of the sail in the back of the animal. In particular, there was an hypothesis in the 20th century that was suggesting that the sail in Spinosaurus was used for thermoregulation. And this is because sails similar to the one in Spinosaurus are also found in early mammals like Dimetrodon. And the bones of these early mammals are incredibly vascularized. This means that a lot of blood is passing through these bones, and therefore having this larger surface could have been useful to warm up blood, and therefore having high rates of metabolism. In the case of Spinosaurus, we were able to reject his hypothesis because even though vascularization is present in the neural spines of the dorsal sail, still is nothing remarkable. Moreover, Spinosaurus was growing really fast, suggesting that the metabolic rates of this animal were really high. Probably it was an endotherm, so a warm-blooded animal. Looking at analogs among modern animals, we found that the crested chameleon is probably the best analog to explain the function of this structure. The sail in this chameleon is used for social goals, in the sense that it's interspecific but also intraspecific. And the meaning means, and the meaning is that these animals are using the sail as a show-off, and it can be used during the mating season. It can be used to recognize individuals of the same species. It's used against predators, and it is also used to resemble a bigger animal. And this is what we think it was happening in Spinosaurus. Also, the fact that Spinosaurus was most probably into water would make a sail as a territory-driven show-off, in the sense that while the entire body is below the surface of the water, the sail could still stick outside of the water, showing to other Spinosaurs or crocodiles or other dinosaurs that in that spot a Spinosaurus was hunting. So, of course, there are many suggestions. We cannot be sure exactly about what was its function, but we can definitely exclude the fact that this animal was cold-blooded, and therefore the sail was not for thermoregulation. So until now, I gave you some hints regarding evidence that put this animal into water. However, we are still missing a key factor, meaning that we still don't know how this dinosaur was swimming in the water column. And the answer came from the tail. This is one of the best tail, better preserved, ever found for any dinosaur. It's fully in 3D, and it has one unique character. The fact that all the vertebrae, from the beginning of the tail up to the tip of the tail, have these long neural spines. This is unique to Spinosaurus. And what these neural spines are doing is to increase the lateral surface of the tail. Therefore, what we thought is that this structure is most probably a propulsive structure, and in other words, was a fin, a caudal fin. We wanted to test and quantify the performance of this tail. So our collaborators in Harvard, Stephanie Fierce and George Lauder, used a robotic setup within a water tunnel to quantify the functional performance of the tail, and also to compare it to the functional performance of other predatory dinosaurs and modern crocodiles, and also salamanders like Triturus. And the results show that the Spinosaur tail performs almost as good as modern crocodiles. Therefore, we can infer that this structure was laterally undulating, exactly like in modern crocs. So if we want to imagine a Spinosaur swimming into water, probably modern crocodiles and alligators are the best analog to study the functional morphology of this animal. So all these results taught us about its ecology and its anatomy. So we wanted to bring back to life this animal. And so Davide Bonadonna and also Marco Auditore helped us to reconstruct the skeleton and to flesh the entire body of this dinosaur. And it's obvious that Spinosaurus is pretty unique, and not only among dinosaurs, but also among all other major vertebrates. There is nothing basically like this. We have a crocodile skull with an animal with a dorsal sail, with a caudal fin, and basically with the limbs of a duck or a penguin. So it's a pretty remarkable dinosaur. And of course, it's a first swimming dinosaur. There is a first, but most probably it will not be the only one. At least we hope so. Now, we wanted to transform a 2D representation of the animal in a 3D model. And this was important not only to flesh out the animal, but it gave us important clues also regarding its life on land. Indeed, when we rebuilt, thanks to Fabio Manucci, the entire animal, we noticed that on land, this animal would have been probably an awkward walker because of the proportion of its body. We calculated the center of mass for the animal, and we saw that the center of mass is pushed far towards the skull. This is atypical in comparison to other predatory dinosaurs because when you are bipedal, basically the center of mass is around your hip. This is the best place where to have balance if you are running around on land. This is not the case for Spinosaurus. And this brought us to hypothesize that at least in part, this animal could have been quadrupedal. So just to wrap up the whole story, this is a 100 years long story that started in Germany and Egypt and ended up in Morocco with this international team, and that completely changed not only what we thought about this animal, but also about ecological adaptations we were just assuming in the entire clade of dinosaurs. As you can tell, it was quite a transformation for this animal, but the whole story surrounding Spinosaurus is much more than simply a scientific discovery, because it's a resurrection of a legacy that was disappearing, Stromer's legacy. But it could also become a true revolution for Morocco. This is because Morocco is starting only now to accept fossils as cultural heritage, belonging to their heritage. And so our collaborators in Casablanca, through our collaboration, were able to institute a first public scientific collection of vertebrates from the Mesozoic of Morocco. And we hope this story of Spinosaurus could actually push Morocco to create a first public exhibition, and so the first museum of natural history in the country. And so with this, I want to thank Yale Body Museum to give me this privilege to speak to all of you. We want to thank, of course, all the foundations that helped us in making this project becoming a reality, especially National Geographic that gave most of the funds for this project. We want to say thanks to Morocco's Ministry of Mines and Energy because they allowed us to make this project and this collaboration reality. And also I want to thank our paleo artists and scientific illustrators that helped us in this scientific project, but also in making this presentation.
Thank you very much, Matteo. I personally really appreciate your presentation, and I'm sure the roughly 290 people who stuck around for it did as well. We do have time for about 10 to 15 minutes worth of questions. Again, the Q&A function is at the bottom of your screen. Matteo, if you want to maybe stop sharing your screen, and then people can, or if there's a reason to refer to your presentation, by all means, share it again. So yeah, please do submit your questions. We'll try to get to as many as possible. I want to kick it off real quick. A lot of folks' first encounter with Spinosaurus was in Jurassic Park. And you and I spoke yesterday about, you gave me the term Hollywood intuition. And I do wonder if you can tell people, as a way to kick this off, like what did Jurassic Park get right? What did they get wrong? And then we'll go from there.
Okay, so what Jurassic Park got wrong is the general reconstruction of the animal, because it's pretty much a bipedal animal running, and it's very much based on relatives of Spinosaurus, so the proportions of the body are actually wrong, but this is something that is more recent than Jurassic Park 3, so our bet in some ways. But what was right is that in Jurassic Park 3, in the last apparition of Spinosaurus, Spinosaurus is swimming and it's completely immersed in the water column to then attack a boat. And this was right, surprisingly right. I remember that I was much younger at the time, and there was a lot of debate about the movie and about, in particular, the skin. Was Spinosaurus able to do it? And most people said no, but actually, apparently, they were right.
Thank you for that. And now we'll get to the real questions, not my own curiosity. So we are getting a number of questions around the relationship of Spinosaurus to crocodiles. Obviously, as one of our attendees mentioned, Kelsey, crocodilians are a good ecological analog to Spinosaurus in many ways, but crocs are often seen as ambush predators, hiding beneath the water surface. So her question is, wouldn't Spinosaurus's large sail inhibit its ability to be cryptic?
Yeah, that's a great question. So thank you, Kelsey. So we have to think about Spinosaurus like a sort of analog to crocodiles in some ways, because it was spending a lot of time into the water. Also, it is not clear how active it was as a predator. This is because we still don't know what was the speed of Spinosaurus into water. It's something that you can quantify and guess. So we don't know if it was a really fast swimmer or not. Also, we think Spinosaurus, contrary to crocodiles, was not ambushing animals that stay inland, like crocodiles do with gazelles and other animals in front of the river, but most probably was more tight and linked to fishes. So we think that even though the ecological analog is right, most probably their lifestyle or their hunting strategy might have been pretty different. But of course, we are not sure. So more tests are needed to understand how good it was.
And before we leave crocodilians, we did get a fairly specific question that maybe you can answer. I guess it'll be hard to answer anything quickly, but we got a question from Kyle around the thinness of the neural spines and chevrons compared to the more robust ones we find in semi-aquatic crocodilians. How would these structures withstand the forces exerted upon them during undulation?
So I always think that interpretations based on only bones are inevitably wrong. This is because bones are tightly linked to tendons and to muscles. Therefore, we don't have to think about narrow spines such as thin structures that are just there forcing through the water a giant animal. We have to think about an elaborate system full of ligaments and muscles that can contract and speed up a swimming process. Said that, we have also to think about animals like tuna or animals really good in swimming that have really thin bones like other fishes. Therefore, it's complicated to know exactly what was going on, but the fact that the neural spines are so thin doesn't mean that the structure is not good enough, because it's a system that has to be evaluated like we did in our paper.
Gotcha. I hope that was a satisfactory answer. And then from our attendee. So I got a great question here from James, age 7, who I think is hanging out with Jessica, who submitted it. James would like to know, and then I'll give you a follow-up to it as well. You can answer them all at once. James wants to know, you mentioned the specimen was likely 50 feet long. How much did it weigh, and how much food would it need to eat? There was a follow-up to that I wanted to add. Do we have any sense of how fast Spinosaurus could run or swim as well?
Okay, so in terms of weight, this is a pretty tricky question. This is because general algorithms and formulas were proposed for weighting dinosaurs. And these kind of formulas are based on the length of the femur, length of the humerus, diameter of dizzy bone. The point is that for Spinosaurus, these variables do not work very well. This is because the legs are shortened, so it's like false positive. Anyway, just to give you some examples, using that kind of formulas would give a weight for Spinosaurus that is around 1.5 to 2 tons. However, our 3D model where we're estimating the mass of the muscles, and also the skin, lungs, and considering the higher density of the bones, will rely around 6 tons. Probably the truth is in the middle. I mean, these are just overall estimation. We cannot be sure, but the general formulas for dinosaurs are an underestimation in the case of this animal. And regarding how good it was on land and how fast it was swimming, we still didn't properly test for this kind of answers. What I suspect is that most probably Spinosaurus was not a really fast swimmer, but it was probably good enough to dominate the waters. And I think that most probably was able to do like crocodilians of sudden movements to catch prey, but we don't know much about it, and it's something that is still in progress.
Gotcha. We had another interesting question. You showed your map of where Spinosaurids have been found around the world. You spent a lot of time talking about this particular one specimen you found in Morocco, but do the other species of Spinosaurs outside of Morocco show aquatic adaptations? similarly?
So this is a great question because it's basically what is needed to be done from now on, at least in my opinion. Because the other dinosaurs were interpreted just like heron-like animals. And so it was just more an assumption. We knew that they are related to water, but everyone assumed that they were still staying outside of the water. But now that we have evidence that at least one of them was swimming within the water, I think now a key factor will be to go back to all these Spinosaur relatives and to find out if these animals were truly just like herons or some of them were already swimming.
Okay. So we're getting a number of questions on a related front. People are very interested in the quadrupedal versus bipedal, locomotion. Do you have any, but can you share any additional information on the modeling for that, or your personal thoughts on how this animal functions?
Yes. So all the entire model is published in the paper, in the supplementary information, and that is available to everyone. So I suggest you to go to check the model that we have available on the base of the bones we used. Said that, I have to say that our estimation is based mainly on a skeleton that is missing the arms. And this is what I would die for to know about this animal. It's a last missing piece. We know more or less everything else about this animal, but we don't have a clear clue about the forelimbs. And I think that will be a key to understand if it was truly quadrupedal or obligated quadrupedal and so on. I think that it was at least a facultative quadrupedal in the sense that, of course, even dogs can walk in two legs if they want to. They can be trained. Said that, I don't think that it was necessarily a bipedal like other predatory dinosaurs. And this is because the center of mass is pushed so far towards the skull. It's much in the rib cage. Therefore, probably it was not able to sustain a bipedal gait for long.
I'm going to try to pose this question to you. I found two on our Q&A that are, one is from another young person who's very excited about paleontology and wants to be a paleontologist someday. And it sounds like a simple question, but it could lead to some interesting discussion. He wants to know, would Spinosaurus be able to kill a T-Rex like it did in the movie? But add to that, I did find another question in here from someone who said, and I've lost it now, that she was under the impression that one of the Spinosaurids found had fragments of a terrestrial animal in its teeth. Is that true? And what does that mean for your theory?
Okay, so starting from the T-Rex Spinosaurus, these two animals never encountered in the geological time, but we have, there was in 2008 a paper that showed a neural spine, one of the big spines in the back of Spinosaurus. It's an isolated vertebra, but it has the neural spine that is broken off from a bite. And looking at the bite marks, people suggest that Carcharodontosaurus, which is the other Moroccan T-Rex size predatory dinosaur, was the animal that inflicted that bite. So we know that these animals were actually fighting between each other, and we also know that there is a vertebra of a spinosaur, a small spinosaur that has a crocodile tooth embedded in it. So probably these animals were also clashing with crocodiles while living together. Regarding the baryonyx, that is referable to dinosaur gut contents in one of these spinosaur relatives. Baryonyx was a spinosaur relative in England, and within the gut, or where the gut should have been, they found scales of fishes and also iguanodon bones. Therefore, it was thought that exactly Baryonyx could be a heron-like animal that was probably fishing, but wouldn't have denied a dinner of a dinosaur, of another dinosaur. And we know that this is plausible. Actually, there is a Spinosaurus itself was probably eating other stuff. There is a pterosaur vertebra from the Henkem that has a Spinosaur tooth embedded in it. So Spinosaurus, even though most probably was eating a lot of fish, did not deny a meal with pterosaurs and other stuff.
Thank you. We have time for a couple more, or I should ask you, Matteo, do you have time for a couple more?
Yeah, of course.
Great. We still have a lot of participants here, and just to give people a sense, we're not missing your question on purpose. We've received, it looks like about 85 questions so far. So again, if we don't get to your question, send it via email or via social media. I'll try to get it to Matteo because I won't know the answer, but Matteo might. And yeah, do keep in touch with us via social media. But 2 more questions real quick. We're getting a number of people interested in you showed that great image of all the nerves and the nerve endings in the jaw and the skull. Folks are wondering if the animal was smelling the prey or feeling it, and if it's feeling it, is that similar to the way sharks hunt? And then are they a good analog for this sort of predatory behavior?
Yeah, so these kind of nerves are giving you kind of a sensitivity to movements. So it's not about the smell, it's more about vibrations that are going around the fluid. In this sense, we know that other marine reptiles like mosasaurs and plesiosaurs had the same kind of system. And of course, we have the modern analog of crocodiles. It doesn't have to do with smell. It has to do with vibrations in the water. In the case of sharks, they have a particular system that is more about electric signals in the water, that is through the ampulla of Lorenzini. And this is a different system. It's about different kind of signal. So if we want to speak about spinosaurs and marine reptiles, crocodiles are the best analog, and vibrations are the key for this kind of sensitivity.
Thank you. So I tricked you a little bit. I'm gonna try to make this happen, but we got 2 more great questions, and then I promise we're done. A lot of folks are interested in that image showed a very short forelimbs, and they want to know how were there any predators that this particular animal had to worry about? Obviously, it was huge, but how would they have gotten away from predators with legs like that? And then if you can wrap up by giving us a sense of the flexibility or the stiffness of the sail. People are wondering if you have an idea on that.
Yes. So when we look at the kind of ecological network that we have in the Henkem, we have to say that it was a pretty dangerous time, in the sense that even crocodiles were reaching 14 meters or 15 meters. And we know of about more than 12 types of crocodiles from the same sediments. We know about 3 or 4 additional predatory dinosaurs and so on. It's obvious that a Spinosaurus would be more vulnerable on land than in water. And there was some work at the beginning of the 2000s that suggested how certain dinosaurs and crocodiles could live together even though they had similar body size. The suggestion was that crocodiles grow really slow, while dinosaurs grow really fast. Therefore, when you think about population dynamics, we can say that something like a Spinosaurus probably had a huge mortality in the earlier stages of its growth. But once it was fully grown, it didn't have much to worry about. So this is the kind of population dynamics you can observe also in tyrannosaurs and so on. And this is work was done on the base of histology by Gregory Erickson. So this is very interesting because it shows you that your growth is linked to your survivorship. Like you have pretty dangerous times in your growth, and you have times where you have not much to worry about. And then regarding the flexibility of the back of Spinosaurus, like the dorsal portion, well, we know that this was much less dynamic than the tail. And we know this because all dinosaurs have a peculiar type of articulation in the vertebrae. And depending how much these articulation are overlapping between them, between vertebrae, you can have basically more or less range of motion. In the tail, the overlap is basically none. That's why the undulation of the tail was really wide. While for the back, we see overlapping. So again, it's probably like a crocodile, where the back is not as flexible as their tail.
Thank you for that. And I hope everyone joins me in appreciating you going a little long. On this, I think we promised about 40 to 45 minutes, and we went almost a full hour. So thanks everyone for bearing with us. Thank you, Matteo.
Of course.
And if you have any questions we weren't able to get to, send them to us via email or via social media. We'd love to hear from you. We'll try to do another one of these next week or the week after. And if you can answer that poll question that popped up about how you heard about this talk, it helps us figure out our marketing strategy for making sure we reach as many people as possible. So one final thank you to Matteo Fabbri for joining us.
Thanks to you.
And check out his article in Nature. And we'll see you all very soon. Thanks, everybody.
Bye-bye.